Let's have a look at your last assessment, the second test on Unit 4, Electricity and Magnetism. The main comment, as I told you in class, is that we struggled with kind of long explanation answers. So we're going to see exactly what those questions needed, and you're going to see more of those during your revision time. So be confident that we will figure it out at the end until the exams. Question number 1, it asks you to create a simple circuit. The reason why it's giving 4 marks is because it's asking for several electrical components. As I've told you, you need to know all the electrical component symbols. Number 1 and number 2, because there is a tricky part regarding the direction of the battery and the LED. So you have your battery symbol, you have your LED, you need to know how the LED looks like, that the LED is essentially a diode, which means it allows current to pass only in one direction, and the way I'm showing it now in this direction, like it's following the conventional flow of current, which is positive to negative, right? So that was another criterion for the mark scheme, and then a fixed resistor next to it. Okay, so that's how you got 4 marks. So not just by the symbols, but also carefully putting the direction of the battery and the LED. Next one, we have a theoretical question that we need to answer about the use of the fuse and the earth metal case of an appliance. The values are not so relevant. So when large current, and you can say more or equal to 13 amps, will pass through the fuse, then the wire inside the fuse will melt, which means it will block the flow of the current, okay? Or in other words, the device is disconnected by breaking the circuit. So that's how you're safe without allowing this extra current to come to you. That's what the fuse does. The earth wire, on the other hand, keeps the case at 0 volts because it is earth, it is grounded, as we say, protecting the user from electrocution by providing this alternative pathway route to current to the earth and not through the user, for 4 marks theory. Next one, yeah, I regretted using this question at the end, but since it's it shows it's an exam question, we could see it now rather than using it for the first time in the exams. So you have the magnetic relay setup with the motor, and you're supposed to make the connections. Most of you got one of the 2 marks, very few of you got both of them. The reason why you got 1 is when you placed the motor as simply connected to the contact Z and W, you kind of missed the fact that the motor also needed some kind of power supply to start on, right? If you added an extra battery in that circuit, that would have been okay. Some of you did that. Not sure if the examiner would have taken that correct, but anyway, the best way to do it is to connect one side of the M, okay, as you can see over here on this side to the circuit, okay. The other side is connected over here to the Z contact, okay, and the upper part, the W contact, becomes also part of the circuit. So when you close the switch, which means current can flow from the 12 volt car battery, okay, then there will be current induced, or in this case the current will activate the electromagnet inside the relay, which will close those 2 contacts and can set the motor in action, okay. So there will be current flowing through the motor. If you don't make that connection, then you need an extra power supply for most of the drawings that you did, okay. So it was tricky, not a great question, but it was worth only 2 marks, so I wanted you to see that this exists out there. Next one was fairly easy. You're given the power of a motor, you're giving the car battery, and you're asked to calculate the current, one of the most fundamental formulas of the unit. Power is equal to current times voltage. The only thing you have to take care of is the conversion of the 1.8 kilowatts to 1800 watts, always checking for unit conversions, as I've told you. So you get 0.15 amps, fairly easy. Next one, E, the same formula with no conversions, just V times I. So that's a gift. 12 volts times 0.35, 4.2 watts. The next one we struggled a bit because apparently we have forgotten what the idea of frequency in physics means, okay? The fact that we learned it in the first unit doesn't mean that we forget that, right? When you learn how to work with fractions in grade 6 and 7, it doesn't mean that you have to restudy them for grade 9 or 10 if you're going to need them, right? So frequency in physics, it shows you basically how many repetitions of a phenomenon are happening in a specific time, right? So one full repetition is happening in one full period. So F is equal to 1 over T. Frequency is equal to 1 over the period, which means period is 1 over F. So you get the number of 1.7 times 10 to the minus 2 seconds, one of the most fundamental formulas in physics, or even ideas, okay, that what frequency is. How frequently do you go to the gym? I go 2 times per week. So I do 2 repetitions, 2 visits to the gym per 7 days, okay? So that's my frequency. When, by definition, you talk about one repetition, okay, the time needed for that is the period of the phenomenon, okay? So the Earth rotates around the sun, okay, one time in 365 days. So one time over 365 days, you convert that in seconds and you get the frequency of our rotation. So a good reminder anyway. Next one gives you the circuit. It tells you how many electrons are passing through and the charge of each electron, okay? So that was, in my opinion, a simple exercise, because most of you knew that I is equal to Q over T, but probably you forgot what Q is. Q is the total charge. So if you have 1.5 times 10 to the 17 electrons, okay, passing through, and every electron has a charge of 1.6 times 10 to the minus 19 coulombs, the overall charge is going to be the product of those two, divided by the frequency, because it says, the period, because it says in one period, so you get 1.4 amps. If, and many of you did get A wrong, but you used the wrong number to calculate B, which means your B was also wrong number-wise, you still got full marks because your solution for B was absolutely correct, but you had you were penalized with points already in A, and then you used that example for your next exercise. So the next one was tricky for most of us. I don't know why, probably because again we don't really understand how a diode acts, okay? So you have to mark with an arrow labeled E the electron flow, the actual electron flow, and with I the conventional flow through the component C, okay? So we see that we have an AC power supply, right? But an AC power supply, which means the current is going left and right, when there is a diode placed, the diode will force the current to pass only in one direction. That's what the diode does, right? So it will only allow it to pass in this direction because this is how the diode is placed. Now, this is the conventional flow of the current, okay? So this is I, which means the actual flow of the electrons is going to be backwards, okay? Next one was a gift. You have the current. You have the current. You have the voltage in the circuit. Simple circuit. Calculate the resistance. Fairly easy. The next one troubled few of us. You have this diagram, this circuit, the thermistor, and you have an EMF of E. The switch closes. Potential difference across the 30 ohm resistors is V30, okay, and the one across the 20 is V20, and the one across component X is Vx, and it's asking for the relationship, the equation that relates Vx and V30. I've added those two extra points on the circuit, like A and B, to show you the edges of each resistor, the thermistor and the 30 ohms, to show you that it's A and B. So Vx, so the potential difference across X, is essentially the VAB, because these are the edges. But the V30, so the edges of the 30 ohms happens also to be VAB, as you can see, and therefore Vx is equal to V30. So that's the equation that relates Vx to V30. Next one, you want the equation similarly that relates Vx to E and V20. You know that if you have an EMF E, okay, then this should be equal to each potential difference across all of the components. And in this case, you have the potential difference across A and B and the potential difference across the 20 ohms. You don't have any other component, right? So E should be equal to Vx plus V20. Vx I call the one across X or across 30, right? And if you want to be super careful, okay, and give the examiner what they want, because it says state an equation that relates Vx to those, you don't stop here, you rearrange the formula for Vx, even though I think you would still have gotten full points. If you want to be careful, just do that and make the examiner happy. You have the same circuit again. State the name of the component. We need to know again the components of an electrical circuit for points like this. This is a thermistor. The temperature of the component X increases. State and explain what happens to the ammeter reading, which means we need to know the components, but also what happens to them when the current is changing, or temperature in this case for a thermistor. The temperature goes up, which means the resistance of the thermistor will go down for the types of thermistors that we are dealing with in IGCSE. If Rx goes down, then the R total, the combined resistance of the whole circuit, will also go down. If you see how I'm going arrow by arrow from here to here and then on the other side. So if the R total goes down, it means that more current will pass through, and if more current passes through, it means that there's a higher reading of the ammeter, and that's how I'm getting my 3 marks with a perfectly answered question. The next one, you have this wire with current passing through. You know the direction so that the current is going downwards, okay? And you're supposed to show on the diagram B how the magnetic field lines would look like, but also the direction. So most of you knew that these are going to be circles. Not all of you made them concentric, so please try, even though you're going to make them probably by hand, try to make them as good as possible. Mention that they are circles, like if you know the shape and they don't look like circles, why not just make a note and say these are supposed to be circles. And an extra tip is, because you know that they're going to be concentric circles, okay, so they all originate and they all have the same center, right? That's what concentric means. Make an extra note and show the examiner that you really know your stuff, okay? Last but not least, show the direction by following the right hand rule, okay? So you all figured out that it's going to be a clockwise by showing the arrows, okay? Next one, we have 2 bar magnets. They create a uniform magnetic field. It's basically the experiment that we did, right? The student wants to reverse the direction of the force on the wire. State 1 change that could have that effect. One could be that you reverse the magnetic field. Another one is that you reverse the direction of the wire. We actually did both in class. The student increases the separation of the poles on the parallel magnet. State and explain. Okay, so now we have some explanation to give as well. What's the effect on the force? By increasing the distance, the field will weaken and therefore the force will be smaller. Okay, so for 2 marks, it's not that long of an explanation. Now 13 was the first kind of long, like 4-mark question that we struggled with, where you have this spring, you have this magnet attached to it, and surrounded by a coil which is connected to the galvanometer to detect the small changes of current. So you pull it down and then you release it. So you have to describe and explain what happens to the needle of the sensitive galvanometer. Okay, so the first observation you can make is that the needle will oscillate. Okay, I hope we understand what oscillate means. Is basically moving left and right as the magnet moves up and down. And now I need to explain the why. So the coil cuts the magnetic field lines, okay, as they are moving in and out of the of this coil. Okay, so it cuts magnetic field lines. This change in the magnetic field induces current, which opposes the change that has caused it. Okay, that's Lenz's law basically. So the induced current will have a direction so that it induces the cause, um, the movement that actually caused it. The last thing to get your full marks is what you mentioned, that you're using Fleming's rule to explain the directions and everything. The best thing to do is to just say that the force, the magnetic field lines, sorry, the force, the magnetic field strength, and the current are all perpendicular to each other. They're all at 90 degrees, right? So that's the last point that's missing from this question. This type of explanation, you will see me already repeating it in this test quite a few times. And what do I mean by this type of explanation? I mean the fact that you have something cutting through the magnetic field lines. This causes a change in the magnetic field, like magnetic flux, as we call it in class, which will induce an EMF on another component. And this induced EMF will have a certain direction, okay, which follows Lenz's law, which comes up later. Last but not least, you talk about the direction, okay, so how you figure out basically the direction of the force or the current on the field, and you don't refer to left or right hand rule or Fleming's rule. You refer to the fact that the three of them should always be perpendicular, like 90 degrees to each other. State for 1 mark the effect if you use a stronger magnet. Of course, you have a larger deflection, okay, so higher values of the galvanometer. Next one is you have this plastic and the copper tube, and you have a very strong cylindrical magnet, and when you drop it through the copper tube, you have current induced in the copper. It should have said induced EMF and not current. So because the current will only be induced, like measurable current, only if you have only if you connect that to a circuit that could actually allow the current to flow, while the EMF will be detectable even with a voltmeter. So I give a shout out to Maddie for noticing this also during the test and making a very insightful comment to that. Yeah, so why there is current in the copper? The magnetic field lines again are cut by the copper, okay? This causes the magnetic field to change, which in return will induce an EMF according to Faraday's law. For 2 marks, that's it. You don't have to take it further, okay? So Faraday's law again. Now the same setup, the same question, but right now you have to explain why the magnet falls more slowly in the copper tube compared to the plastic tube. The fact that it falls more slowly, to me as a physicist, means that there is probably an opposing force against gravity, an upward force in this case, okay? So now I need to explain what creates this force, which you probably already know where I'm going with it, right? Again, same explanation. As the magnetic field lines are cut by the copper, which means the magnetic field flux is changing, according to Faraday's law, this will induce an EMF which should have a direction so that it actually opposes the actual motion, the one that actually caused in the first place the change of the magnetic field. Again, referring to Lenz's law. You see how fundamental Faraday's and Lenz's law are for these type of explanations. So please revise them and practice with these questions, and hopefully they are clear to you. If not, definitely come back for more clarifications, okay? Next idea, what do we have here? Component A for this generator, slip rings. The diagram, yeah, shows the motion, so you know the direction of the rotation of the coil of wire, and you have to show on the diagram, you draw an arrow to show the direction of the current, and you have to explain your answer, okay? So we've discussed that we're using the right hand rule, okay? So field lines, from north to south, the motion is pointing upwards. So what's left for me is that the current is moving upwards in this case, so it's going clockwise, okay? You can see my fingers, but what you can say on the paper is that the direction of the field, the motion of the force or the motion of the wire, and the induced current should all be perpendicular to each other, okay? And that's how you basically explain the Fleming's right-hand rule. So this one, plus mentioning Fleming's right-hand rule, definitely guarantees you that no one can question the 2 marks and you get full of them. Explain another tricky question, how the rotating coil in the diagram continuously causes the galvanometer needle to show an AC current. So as the coil rotates, it cuts the magnetic field lines between the magnets, okay? This, you see, again, I'm repeating the same story, right? Same explanation. This induces an EMF in the coil. In return, this will produce a current in the galvanometer, detected in the galvanometer, via the slip rings and the carbon brasses. The direction of the current, last point, changes with each 180 degrees of rotation of the coil, okay? So basically these are the 4 points for B. Now we go to the simpler, these were the more challenging questions, challenging in terms of properly explaining, right? Describe 2 advantages of high voltage transmission. I have a couple here. Less heating on the wires, less energy loss, lower current, meaning thinner wires, so less resistance of those, fewer power stations. There are even more to think about. Next one, you have this transformer. First of all, name the device. This is a step down transformer because we have more turns on the primary coil and less on the secondary, so we're stepping down the voltage, so step down transformer theory. The material used for the coils, copper, also theory. And now the same setup, you have to calculate simply the number of turns on the secondary coil when you know the other 3 variables. So the most basic formula, you solve it carefully for number of turns on the secondary, you get 400. Most of us got that right. And the last 2 theory questions, which were okay-ish, I would say, but also some things to bear in mind. Explain why electrical power is transmitted at a voltage of 400,000 and not 22,000. They're both high, but what's the point of having one over the other for 3 marks, okay? So high voltage results in low current, okay? Why is that? First, when P is constant, we know that P is equal to V times I. So when V is high, then current should be low, okay? Now, why is this important? You mentioned that, but why is it important? Because this limits the power losses. Why is this limiting the power losses? You can either refer to P equals I squared times R. So low current, low I means even lower power losses. Or if you don't mention the second formula, the I squared times R, just by saying that with low current, we are avoiding less heating effects on the wires, which means less energy losses, okay? So one or the other, but the formulas are always helpful. Explain why the voltage of the supply, back now to the transformer, the supply to the primary coil of the transformer must be AC to produce an alternating or change the magnetic field so that the current is induced in the secondary coil, okay? So if you want to induce a current in the secondary coil, you must have a changing magnetic field on the first one. DC would not work. We said that, we highlighted that a lot in class, okay? So these are the questions. Please have a close look at them. Like, watch, this video is going to be a long one, okay? I've been talking for some time now, and some questions definitely require more attention, okay? And come back to me with questions should you